So, week 10, you made it. We're going to talk about coastal processes and landforms this week. We'll start out with just some general concepts of oceans, basins, water, and the movement of water and how water transports material. And then we'll talk about the different landforms that are created from erosion and deposition and different types of environments. So one just kind of basic understanding is, I think everybody knows this, that 90%, 97% of the Earth is ocean water. And of that 96% of that water, 3% is dissolved solids or salts in the water. And so this talks about the salinity of the water is that concentration of dissolved solids. And the salinity of ocean water varies, and it varies depending on the amount of rainfall that's coming into the water, the amount of evaporation, and the amount of other fresh water flow, or salt water for that matter, flowing in or out of an ocean body. So we talk about water that's called brine when it is very salty, higher than the average, which higher than 3.7. And you'd see this in places like the Sargasso Sea, the Persian Gulf. And the Persian Gulf is about 4%, and this is mainly because of very high evaporation rates. So if we look at a couple Google Earth images of this area, you can see that there is extraction of minerals, and you can also see some changes in sea extent. And I'm sorry, I meant the Dead Sea. So if you go into Google and you type in, search for the Dead Sea, under the Global Awareness link, there's the UN Environmental Programs list of concerns. And so this area pops up. I'm going to click that, or not. I'm going to click outside of here. There you go. So they have identified this area as one of the UN focus areas. And they've got some nice information on the ecosystem changes that have happened in that area. So the water dropping here because of evaporation and because of using the water for populations, and then by creating this evaporation ponds to mine, what are they taking out of here? Anyway, creating the evaporation ponds for producing salt has increased, and it furthers evaporation. So kind of an interesting concept, and I'm wondering if we can see much if I go into, so let's go back in time here. So that's 2002. It's pretty pixelated. And then we can go up a little bit. Let's see when it starts to really focus in. Now, yeah, so that's 2005. And then I'm just looking at 2007 on the time bar here. Yeah, so it looks like there's been some expansion of the area. Anyway, so just looking at how fragile some of these environments are. One of the things that you'll see is as a result of evaporation is the water evaporates and leaves behind these evaporites or salt formations, crystals, and you would see this at Mono Lake in California as well. Mono Lake is not in California, is it? Check that one. Dang, I was right. It is in California. Well done. You see water that is very briny in the Great Salt Lake. Here are people in the day floating in the water. You can't sink because it's got a lot more mass to it. The opposite of brine then is brackish, and this is water that is less than the average salt content. And you see this in areas where there's very low evaporation rates, maybe large amounts of fresh water flowing into it, and in cooler areas. So that would be places you would have low evaporation. So Baltic Sea would be a great example of a place where the water is going to be more brackish. You also see that along coastlines in those inner intercoastal areas between streams coming out into the coastal environment and tidal water moving upstream. You'll get brackish areas. When we look at coastal areas, one of the things that we often are concerned about are islands, especially now as we look at global climate change and rising sea level. There are many islands that are at risk. There's three major ways that islands are created. There's continental islands, islands from coral reefs, and oceanic islands. Oceanic? I think that means, oh yeah, okay. Well, I would have called it tectonic, but anyway. The prior book calls them oceanic. So the Hawaiian Islands are a great example. We talked about a hot spot in the mantle allowing lava plumes to reach the surface, creating these very large, in the case of Hawaii, shield volcanoes. And as the continental plate moves away, it drags that island away from the hot spot, and a new island is forming again. Actually, these do not have to be oceanic hotspots. To form an island, they do. But Crater Lake is not Crater Lake. Yellowstone is over a continental hotspot, but that's neither here nor there. So that's one way islands are formed. Often, when you have an island, you will be able to, or the island will form a reef because coral can attach itself to the amount of light needed in at a correct elevation around an island, and form a fringe or a reef. And over time, as the island may erode from surface wave action back down to sea level, you may be left with kind of an atoll or a ring of just the former reef. And then when everything's gone except a underwater seamound, that's called a guyot. We're having environmental problems with coral reefs as well. Coral seems to be a very, very fragile ocean species. They respond to disturbances in the amount of pollution in the water, the amount of sediment, so chemical pollutions. TMBRAT. Wow. Let's see if I can get that in there. Good Lord. There you go. Changes in salinity and other erosion, increased wave action, or things like that. So it's called bleaching, and these coral reefs become dead, so there's no more live coral, and then become more vulnerable to erosion. And the coral reefs themselves act as a border or protector for island coastlines. So here's some locations of bleaching hotspots where coral bleaching is a concern. The third type of island are continental islands, and these form as a result of the continental boundary just being inundated with water. So a great place to see that is up in the Seattle area. So here are a couple little furrows island, and depending on sea level, these may or may not be islands. So say 18,000 years ago at the glacial maximum, there was so much more water on the continents as held in ice that you would have been able to walk from one of these little mountains to another one and not be in water. So many of these kinds of islands are just an extension of the continent itself. Actually, all of these up here. So that's the continental island process. Oh, and I moved my thing. Let's move this, see if I can move this back. Hold on. There we go. When we look at a beach, there's ways to talk about the beach in terms of the whole profile. So the littoral zone is that area from about 200 feet below the water surface. That's kind of the area where surface waves no longer mix with the ocean bottom, all the way back to the highest area of coastal processes. So that's called the littoral zone. And then the coast itself is from kind of the high water or high tide line or surf zone back into kind of the dune or coastal processes. So when you're up in the low tide or in the shoreline area, the waves are touching the bottom, the sand. There's a lot of mixing. If you go out into deeper water, as I said earlier, about 200 feet, the generating waves are usually not big enough to mix with seafloor sediments. We look at the average sea level or mean sea level, and this is kind of the average tidal change over a long period of time. And it's a fairly accurate way to talk about changes in that high tide to low tide area on the beach zone. So we're talking about tides. When we look at tides, tides are a product of the external forces of the alignment of the Earth, the Sun, and the Moon, and also the centrifugal force of the Earth spinning on its axis. So the Moon has about a cycle of 29.5 days. There's a full rotation of the Moon, and as it orbits around the Earth, it tends to exaggerate that bulge or pull that bulge of water by gravitational forces along with it as it moves around the Earth. And the centrifugal force then also causes that flattening of the tide at the polar or the opposites, and pulling of the water bulge toward the edges. And so this happens about every 12 hours. We have 2 high tides and 2 low tides. They don't happen exactly at 12 hours. They're about 24 hours and 50 minutes is the entire cycle. And that's why high tide and low tides change. And that's why tide charts are easy to predict. Now, sometimes you get an exceptional alignment of the elements where you get extra gravitational pull, and that's called a spring tide when the Earth, the Moon, and the Sun are lined up in a straightish line, and that really exaggerates the high tide. So you get the extra high tides, and that is called a spring tide or a flood tide. The opposite, when you get the Moon pulling the gravitational bulge one way and the Sun pulling perpendicular, you get a neap tide or an extra low tide. And not all tides are the same. The Bay of Fundy is said to have some of the highest tidal changes in the world. So here is the Bay of Fundy, and they have about a 45 to 50 foot change in tidal elevation during their high and low tides. So there are many places in the world that have used that change in tidal motion to generate power. And as you may know, they're trying to do that off the coast of Oregon. I think Oregon State has some research generators. But when you have a bay, like the bay, as in the Bay of Fundy, so where is that going? So there's water rushing into this area, and the channel right here is very narrow. You can put turbines across that channel and actually generate water. So here's one in an area in France where they're trying to use just the regular tidal motion to generate energy. There's just a very cool phenomena called a tidal bore, and you may see that if you're out in the Siuslaw. Sometimes you see a standing wave at the mouth of the river. So as the water from the river is flowing out to sea, but the tide is coming in, you get this wave that just kind of stays in place, and it's become a great recreation place, and great recreation destination in many places. And the Amazon has a 12 to I think 15-foot high tidal bore, and people will surf from one side of the Amazon to the other. There's 20 to 30-minute surfing rides. So there's huge competitions when you have those kind of phenomena. So water moves just by process of the tide coming in and out. So if you have low tide, sediment is farther out. As the tide comes in, it will move sediment with it up onto the beach. And so you have that daily diurnal movement of water up and down. The other movement that we're all familiar with are waves. And so waves are generated by wind causing friction on the surface. And so it's kind of like if you blow a cup of coffee gently, you can see those little waves or ripples. And so sometimes you may have just little, very light surface ripples across the surface of water. But if you have a lot of wind, you can generate bigger waves, and these set up a process of oscillating circular movement in the water, or swells. And so the bigger the storm, the more wind, the bigger the wave. And so we talk about storms as generating regions for waves. And when you have a generating region, the wave, let's say you have a big storm in the middle of the Pacific. So the waves are generated out in all directions. They'll be larger in the direction of the predominant direction of the wind, but they do set out this radial pattern. When we look at a wave, we talk about the crest and the trough. So the crest is kind of the top of the wave or the swell. The trough is down in between, and the wave length is the difference between the two crests. So if we're looking at waves or wave generation out in deep water, so say at that 200 feet or more where there's no mixing of the bottom sediment, the wind generates what are called swells, and these are just kind of round oscillatory motions within the wave, and there's not a lot of forward movement. I used to have a great little video that showed you a ping pong ball kind of sitting on a column of water, and you would watch that ping pong ball kind of dip down at the depth of the wave and come back up, and it might move forward a little bit, but mostly it was just kind of staying here, kind of slowly circulating within its own swell. And so this is kind of that oscillatory movement of waves. And waves come in, as I said, they come in to the shore perpendicular to the generating storm. So let's say the generating storm is out below the slide, kind of where I'm waving the little yellow hand here. And as those generating swells come toward the coastline, they begin to be bent or diffracted by running into things in the water. So other islands or mountains or reefs or jetties, anything that would kind of diverge that swell will change the direction of the wave. And so here's an example. I think you can see it a little bit as the waves are coming in from the upper left-hand corner of this slide, and they run into this point of land and this little island remnant. You can see that those waves are no longer straight. They've got a bend to them as they've been kind of changed as they flow through that area. So when we talk about sediment transport, there's a couple ways. This is the terminology, I think, in the reading is a little different. They talk about it as longshore drift, longshore transport, littoral drift. And basically, what this is talking about is the zigzag movement of sand and sediment down the beach along with the major current. And so if we look at this really nice diagram, you can see that the effective wave direction, so that's the generating area of the storm, and the waves are coming into the coastline at an angle because they've been refracted from maybe a sea stack out beyond the slide. So they get bent, they come into the shore at an angle, wash up on the shore at an angle, but they come back down into the water under the force of gravity perpendicular to the beach drift. So as the wave comes into the shoreline, it picks up sand and gravel, brings it up to the shore. The wave slows down, just like in river transport. There's not as much energy. The sand drops out. The wave flows back into the water, gets regenerated, comes back up on the shore, drops sand again. And so if you were to drop that same ping pong ball up here in that surf zone, you would see that ball kind of moving down the shore in this direction. So sand gets transported down the shore. So we were talking earlier about this no mixing zone and what happens when that swell gets into the surf zone. So so I'm just learning how to use the draw program here, and there's some really bad drawings, but we're going to just, hopefully this will be so fuzzy on the video that you won't be able to really see how badly this is drawn. So anyway, so the arrow is the general direction that the waves are moving. Here's your oscillatory swell. And as the swell moves into more shallow water, the swell begins to touch bottom or feel bottom. And that friction causes the bottom of the wave or the bottom of the swell to move slower than the top of the swell, which begins to oversteepen and elongate that swell until the swell actually has a crest or breaks, and that's called the wave of translation in the surf zone. So depending on how big the swell is, this could be mixing all the way out here and cresting because you have a really big storm, or it could be a very gentle waves and not break until you're very close to shore. And so here are some examples of these waves breaking, beginning to oversteepen and break here. They reform and they break again and again as they move in toward the shore. So basically, kind of remember that the whole process of moving sediment comes from the abrasion of water, removing particles, the movement of sand up and down, the higher energy the wave, the bigger the wave, the more power it has, the more energy it has to do work. The calmer, the quieter the wave, the less energy. So you're going to have erosion where there's a lot of energy, deposition where there's less energy. So that's kind of that whole processes, and the next part then we'll talk about the different landforms.